Space weather refers to the environmental conditions in space influenced by the Sun's activity and its interaction with Earth's magnetic field and atmosphere. This dynamic and complex phenomenon encompasses a range of solar and cosmic events, including solar flares, coronal mass ejections, CMEs, solar wind variations, and geomagnetic storms. The science behind space weather involves solar physics, plasma physics, magnetospheric physics, and atmospheric science, aiming to understand and predict the impacts of these events on Earth and space-based technologies. Solar activity and solar wind. At the heart of space weather are processes occurring on the Sun's surface and in its outer atmosphere, corona. The Sun continuously emits a stream of charged particles known as the solar wind, which flows outward in all directions through the solar system. Variations in the solar wind's speed, density, and magnetic field strength can influence space weather conditions near Earth. Solar flares and coronal mass ejections, CMEs. Solar flares are sudden releases of energy and radiation from the Sun's surface, accompanied by the acceleration of charged particles. These energetic bursts can cause radio blackouts and radiation storms in Earth's ionosphere. Coronal mass ejections, CMEs, are massive expulsions of plasma and magnetic field from the Sun's corona into space. When directed toward Earth, CMEs can trigger geomagnetic storms and auroral displays, auroras, by interacting with Earth's magnetosphere. Geomagnetic storms and auroras. Geomagnetic storms occur when CMEs or high-speed solar wind streams interact with Earth's magnetosphere, the region surrounding the planet influenced by its magnetic field. These disturbances can cause fluctuations in Earth's magnetic field and induce electrical currents in the ionosphere, affecting radio communications, satellite operations, and power grids. Auroras, such as the Northern Lights, Aurora Borealis, and Southern Lights, Aurora Australis, are colorful displays of light visible near Earth's polar regions. They occur when charged particles from the solar wind collide with gases in Earth's atmosphere, emitting photons of light. Auroras are not only visually stunning but also provide insights into the interaction between the solar wind and Earth's magnetic field. Impacts on technology and society. Space weather events can disrupt satellite operations, communication systems, including GPS, and power grids on Earth. Magnetic storms induced by solar activity can create geomagnetically induced currents, GICs, in power transmission lines, potentially leading to equipment damage and widespread blackouts. Protecting critical infrastructure from space weather requires monitoring and forecasting capabilities to mitigate potential impacts. Monitoring and prediction. Scientists monitor space weather using ground-based observatories, space-based satellites, and computer models that simulate solar and geomagnetic activity. Organizations like NOAA, National Oceanic and Atmospheric Administration, and NASA provide space weather forecasts and alerts to government agencies, industry sectors, and the public. These forecasts help spacecraft operators, airline pilots, and utility companies prepare for and mitigate the effects of space weather events. Conclusion. In summary, the science behind space weather involves studying the Sun's activity, solar wind dynamics, and their interactions with Earth's magnetosphere and atmosphere. Understanding space weather phenomena is crucial for protecting technological infrastructure, ensuring space mission safety, and advancing our knowledge of solar-terrestrial interactions in the dynamic environment of our solar system. Ongoing research and monitoring efforts continue to improve our ability to predict and mitigate the impacts of space weather on Earth and space-based activities.